In this video, we're going to talk about evaluating a transfer function. You can see here I've given an equation for some arbitrary transfer function h of j omega, and my goal is to evaluate it at the frequency of 1,000. And on the on the left-hand side, you're seeing the Bode plot for that transfer function. Okay, you're seeing the magnitude plot. So what I'd like to do is to discuss how to evaluate h of 1,000, but I'd also like to talk about how to do it intuitively, not just how to do it numerically. We'll do it both ways. So the first thing I'd like you to notice is that other than this j omega term in the numerator, other than this term, every term consists of a j omega term and a 1. And the simplifying assumption that we can make is that if omega is small, then we can just assume that the binomial equals 1. And if omega is large, whatever that means, then we're going to stick with the j omega term. We're going to say that the j omega term is so big that it effectively dwarfs the 1, and we can ignore the 1 without introducing too much error. Okay? And generally speaking, the point at which omega goes from being small to being large is when it exceeds the value that's in the denominator, okay, that 100. So in other words, for this term down here, when omega is a lot smaller than 100 rads per second, we're going to assume that it's so small that we just keep the 1. And when omega is a lot bigger than 100 rads per second, we assume that we're going to get the j omega over 100 term. All right? So that's effectively how these things work, right? We have a pole that or I shouldn't say pole, we haven't really talked about that yet. But effectively what we have is two terms that are vying for control, and essentially only one of them can be in control at a time. So let's go ahead and figure this out. We'll start with the estimation method. Okay. So in the estimation method, I'm going to go term by term. I'm going to figure out which term is winning. Okay. So let's see. So we've got h of j omega is approximately equal to, sorry, let me back up a second. H of j times 1,000, we're dealing with a specific frequency, is approximately equal to. So the first term is j omega. Well, there's no term there to win. I mean, there's just one term. It's just j omega. So we're going to keep that as j 1000. Now we've got the next term is j omega over 5000 plus 1. Now in this case my omega is 1000, which is a lot smaller than 5000. So I'm going to assume that the 1 term is a lot bigger than 1000 over 5000, that's 0.2j. So in other words, in this particular case, it'll be 0.2j plus 1, and I'm going to assume that, well, we can basically ignore the 0.2j. Let's just keep it at 1. I can't truly ignore it. I mean, it's still there, but just if I'm trying to get a quick and dirty back of the envelope calculation, I can assume that it's just a 1. And now we go to the denominator. Okay, so over here, now we're dealing with this term. Now if I let omega equals 1,000, the j 1000 term will totally dominate the 1. So this will be j 1000. And then finally we're going to get the term over here. Once again, the 1000 will be a lot bigger than the 1000 over 100. Will give us 10j, which is a lot bigger than 1. So I'm going to assume that this is essentially 10j. And now, look how easy it's going to be to get the magnitude of this. Okay, the magnitude is essentially going to be 1,000 times 1 in the numerator, divided by 1,000 times 10 in the denominator, and that's going to give me 0.1. And if I want to get the phase, it's still going to be phase of numerator minus phase of denominator. So the phase of the numerator is going to be the phase of the j, which is 90, plus the phase of the 1, which is 0, minus the phase of the 1000j, which is 90, minus the phase of the 10j, which is 90. So that works out to approximately minus 90 degrees. All right? So that's all well and good. Now let's go and get the precise method. And the precise method is literally plug and chug. Okay? So if I want to get the magnitude, it's going to be, let's say it like this, the magnitude is going to be equal to, it's going to be the magnitude of each one of those terms. So the magnitude of j omega is just omega. The magnitude of j omega 5000 plus 1 is going to be, the square root of there's no j, the square root of omega over 5000 squared plus 1. And in the denominator, it's going to be the square root of omega squared plus 1. And finally, we're going to have the square root of, omega over 100 squared plus 1. And then we're going to let omega equals 1000 and evaluate. And I did this calculation ahead of time. You should do it yourself. When I worked it out, I got that h was, the magnitude was 0.1047. Okay? And what's gratifying is that the true value is pretty close to the estimated value. Okay, doing that estimation really didn't leave us all that far off track. Okay, now let's try the phase. Okay, so once again, I'm going to go term by term. I'm going to get phase of numerator minus phase of denominator. So first I've got j omega. So that phase is 90 degrees minus, plus the inverse tangent. And now I'm dealing with the j omega over 5000 term. So that's going to be the inverse tangent of omega over 5000 minus the inverse tangent of omega, so now I'm in the denominator, minus the inverse tangent of, omega over 100. And once again, we're going to let omega equals 100, and 1000, I beg your pardon, and evaluate. And that gives us, where's my answer? I did this number ahead of time, you should do it yourself. That gave us 72.9 degrees, negative 72.9. So in this case, I was still pretty close, but not nearly as close as I was with the magnitude. The phase tends to be a little bit more inaccurate when you do the estimate, but still I'm in the right ballpark. So again, the purpose of this video was just to kind of show you once and for all how to get from beginning to end through one of these calculations. And there you go, an estimated answer and a precise answer.